All right, so we're going to just continue here where we left off, although you'll see that I've drawn something different that you might want to add to your notes. Um, I do not have an equation written on my screen right now, and the easy way to figure that out is that equations always have equal signs, and you'll notice I don't have any equal signs here. So we're taking a little break from equations and solving equations so that we can examine quadratics a little bit more closely. And specifically, I want us to figure out if there's anything in common between the expression here on the left and the expression on the right. Now, more obvious than similarities is the differences. We have one equation, the one on the left, has what we call three terms that are added together. X squared is a term, 6x is a term, and 9 is a term. And we add them all together, creates a quadratic. On the right-hand side, we have two quantities in parentheses that are being multiplied. So even just in that, and actually in the left, we see an x squared and an x term. On the right, we see two x terms. So very different expressions. In order to examine more closely if they have anything in common, we're going to take the one on the right and see if we can simplify it. And if you recall from the first section, we can simplify this using the distributive property, and I call it the double distributive property. You may also know it as FOIL. So what I do is I take x, I multiply it to the first term and to the second term. So x times x gives me x squared. X times 3 gives me 3x. Then I need to multiply the second term because we have to make sure everybody gets a chance to be multiplied. So share it with the first and the second term. 3 times x is 3x again. And 3 times 3 is 9. Now you'll notice that these two middle terms are like terms. They're both x values. So instead of saying 3x plus 3x, I could just call that 6x. Put them all together, lump them together. So that would be x squared plus 6x plus 9. That's the value we get when we do what we call either the double distributive rule, double distribution, or you may be more familiar with it as FOIL. First, outer, inner, last, either way. Okay, so look at what we got, x squared plus 6x plus 9. If that sounds familiar, compare that to what we have over here. And you'll find that surprisingly, perhaps, or maybe not if you remember where this is going, the quantity on the left and the quantity on the right are actually the exact same value. Now, if you don't remember this from a previous class, that's probably a bit surprising because there's very little in the pink here, so in the initial part of what we wrote, that looks similar. They look like completely different quantities. But when I use my math knowledge to simplify, we find out that they actually are worth exactly the same. And this is often kind of a complicated thing to people, like why are these two the same? How can you say that they're the same? And the way I'm going to describe it, oops, I'm going to clear this, is I'm going to use an analogy to area. So before we talk about this, let's just do a little review on area. Let's say I have a rectangle and I want to find the area of the rectangle. What I do is I take the width and I take the length and I multiply them, right? So I would take width times length and that would equal the area. Or I could actually, let's say that this was on graph paper and all of these were divided up into little squares. I could actually take the squares and I could count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I would get 15 squares. And actually, if I multiplied my width times length here, it would be 3 times 5. So we find that either I could say 3 times 5 equals the area, or I could say 1 plus 1 plus 1 plus 1 and add them all up also equals the area. In both cases, I get 15 as the area of this rectangle. But in one, I used the dimensions I multiplied them to find the area, and in the other case, I found the inside quantity and added it up. So keep that in mind and check out this similar picture. We'll say that this is a mystery rectangle, and actually, in this case, it's a square, so not always, but in this case, it's a square, so I'll make it look like a square. And let's think about our equation that we were talking about before, x plus 3 times x plus 3. And let's pretend that this is the width and the length of our rectangle. We'll call it x plus 3 and x plus 3. And x is like the mystery length, so we'll say this is 1, 2, 3 plus whatever the mystery length of x is. So that's what this length is, 1, 2, 3 plus x. And then on this side, it's the same thing. Here's x plus 1, 2, 3. Let's make a little bit of a grid in the same way that we made a grid for the rectangle to add up the squares inside of it. And if you've ever used algebra tiles, essentially that's what this is. And let's think about the pieces within this rectangle. This first piece right here, actually let me get a different color. Back to our pink color. So this first square, actually, make sure that we see where it ends, has dimensions of x by x. These smaller, again, I'll use a different color, these smaller rectangles have dimensions of, this is 1, 2, 3, so 1 by x. So each of these are 1 by x. Oops, that was kind of messy. And the same thing here, each of these have dimensions of 1 by x. And each of these, what color haven't we used? We'll do green. Each of these smaller squares are 1 by 1. If you think about the width that we defined, this is a width of 1, this is a width of 1, so this is 1 by 1, 1 by 1. Okay, let's think about what each of these are worth then. If this pink square is x by x, that makes this an x squared, because x squared is x times x. The area of the pink is x squared. Each of the orange ones are x times 1, an area of x times 1, so that means they're each a value of x. And then each of these green squares are a value of 1, because they're 1 by 1. So their area value is 1. Knowing that, what is the area of this figure? Either we can say the area is width times length, or we can say the area is x squared plus a bunch of x's, 1, 2, 3, 4, 5, 6 x's to be precise, and a bunch of 1's, 1, 2, 3, 4, 5, 6, 7, 8, 9 1's. So either I can define the area as the width times the length, or I can define it by the pieces added up together. And again, just like we described in earlier in this video, we find an equality that shows that x plus 3 times x plus 3 is exactly the same as x squared plus 6x plus 9. The actual mathematical value is the same. So keep that in mind. We're going to talk about how that will be useful to us in solving equations in a moment, and we're also going to be working with these problems, working on practicing. This is called factoring, the process of factoring. We're going to be working on that in class. But I want you to write this down in your notes as sort of the foundation for how all of this works.